All right, the next thing we're going to look at when it comes to graphing polynomials is end behavior. An end behavior of a function is what the graph is doing on the far left and far right ends. That's why it's called end behavior, when the x values are either very large or very negative. So as x is approaching, large numbers like 100, 1,000, etc., sometimes we can tell this behavior even sooner than that, or on the other end, -50, -100. So polynomial graphs will always go up towards infinity or down towards -infinity on the ends of its graph. Those are the only options. So how are we going to tell what it's going to do? Okay. We will use what we call the leading coefficient test. Okay. And so the way you're going to do this is you're going to find the leading term, the highest power term in your polynomial, and you're going to look at that coefficient. Okay. And it's going to tell you whether the graph is going up or down on the left side and the right side. Okay. So we need the leading coefficient and we also need the degree. Okay, so those are the two things that will help us. So if n is your degree, okay, if it's an odd degree and the leading coefficient is negative, the graph is going to go, don't know what it does in the middle, but it's going to go up to infinity on the left side and down to -infinity on the right side. So up on the left side and down on the right side. And if the leading coefficient is positive, but the degree is still odd, but now the number in front of that highest term is positive, it's just going to switch. So it will go down. I don't know what happens in the middle, but then it will go up on the right. So it just switches. Okay. So when the degree is odd, the two sides do opposite things. One goes up and one goes down. Right? And then which one is which, it depends on whether the leading coefficient is positive or negative. So the difference for when the degree is even is it's going to do the same thing on both sides. So if that coefficient is negative, it's down on both sides. Again, I don't know what's happening in the middle. This could just be a parabola, or it could do a bunch of turning points in between. I don't know. So this is going to be down on both sides. And that will just switch again. If you have an even degree and a positive coefficient, it's up. Don't know what happens in here on both sides. And I want to just introduce to you a little bit of notation. We use an arrow notation to write this. So I'm going to come in with a different color here. And we will say x approaches -infinity. The arrow means approaches. And so as x approaches -infinity basically means as x gets more negative, right? It's going this way on the graph. And then we could say f of x, which would be the y values, approaches. Again, we use the word approaches for the arrow. F of x approaches, let's see, if I were going to take this first situation, as x goes to -infinity on the left side, what are the y's doing? They're going to infinity. So that means the y values get larger. Without bound is a term you might hear us say, us mathematician type people. But without bound means there's no no highest number. It's just going to keep getting bigger and bigger. So this notation is a compact way to say something like this. So as x approaches positive infinity, so on the right side, f of x approaches negative infinity. In this particular case, as x gets bigger positively, y's get more negative, they go down. So if I did one more arrow notation, I'll just put it over here for this first box in the second column. X approaches negative infinity, f of x approaches negative infinity as x goes to the negative direction, the y's go down. And that would be the same as x goes to the positive infinity, the y's also go down. So x approaches positive infinity, f of x approaches negative infinity. So this is often, this arrow notation is a way to describe end behavior without using words like up and down, kind of a notation that we use. And that notation will carry on when you're in calculus and you start doing limits. You'll start using that same notation. So it's good to get used to it now. All right, so here's what we're going to do at this point to graph polynomial functions. As I said, we can't really determine exactly where those turning points are. You need to learn how to take a derivative in calculus, and we don't have that yet. But we can do enough that we can get pretty close. So here's what we're going to do. We're going to start by factoring our function, finding the zeros or the x-intercepts by setting that function equal to 0. Use the multiplicities of the zeros to determine the behavior at those intercepts. So does it cross? Does it come up and touch it and come back down? We'll find the y-intercept as well and place that on the graph. We'll determine the end behavior by looking at the leading term and then put all of those together to sketch a graph. Okay. You won't be able to find exactly where it turns. You'll be able to tell, oh, it turns somewhere in there. So you can pick like one number somewhere in that interval to try to give it yourself a sense of how high or low it does go, but it won't be perfect. And that's okay. That's the expectation at this point, is this is as far as we can go. So let's go ahead and work on the first one. We want to sketch a graph of this function and include all the intercepts. So the first thing we said we were going to do is factor it. And that will allow us to then find the x-intercepts. So I'm going to have you take a minute to go ahead and factor this. Press pause, give it a try. All right, how did it go? Since there were 4 terms, I thought, well, I'll at least try to factor by grouping. And it worked. So I went ahead and factored out the x plus 3 and then broke up this one by using the difference of squares. If you didn't do it that way and you did some possible rational roots and found one that worked, that's okay too. You should have gotten down here to the same place. So now that I've factored it, for my x-intercepts, I'm going to set this equal to 0. And then that gives me -3, -2, and 2. And these are all multiplicity 1, right? So that means if I were going to, I'm going to draw myself just a quick x and y. The reason I didn't give you a grid for these is sometimes the numbers are really big, and it makes it really difficult to draw it in a grid because you have like the x-intercept is down at -30. So I find it's almost better. It won't always be drawn to scale, but you can label where the correct values are or what they are. So I'm going to have an x-intercept at -3, -2, and 2. So I'll give myself, oopsies, I didn't mean to do that. I'm going to give myself a couple tick marks here. Here will be my x values. Again, they're not going to be perfect, but that's okay. So at -3, I'll have an intercept. -2, I'll have an intercept, and 2. And since all three of these are multiplicity 1, I know that this graph is going to cross. Now, I don't know yet whether it's going to be this way or this way, so I'm going to do a little bit more work. Okay. So what does our list tell us to do next? We factored, we found the intercepts, we've used the multiplicities, we know what that behavior is going to be, so we're going to find the y-intercept and determine the end behavior. Okay, so the y-intercept should be pretty easy. You're just plugging in x equals 0, which gives me straight to -12. I told you, see that, I'm not going to be able to tick mark that down here, so I'll just write -12, have it be kind of low there. So that tells me already there's no other place where my axis, my graph is going to cross my axis. So I know that this graph has got to be coming down. Now, which means it's going to be crossing at those two intercepts like this. See, kind of power of elimination. Now, am I sure that this is the lowest point? I am not. It could be that it goes lower here and is coming back up, but I don't have a way to determine that at this point. So if I have one point in there, I'm going to go ahead and use that as my turning point. Okay, so that's what I mean when I say the specifics are not perfect, but we get a good idea. All right, so then the last thing we're going to talk about here is our end behavior. So I'll write it with arrow notation. I'm going to think about what's happening on the left as x approaches -infinity and what's happening on the right as x approaches infinity. And to do that, I'm going to look at my degree. It's an odd degree. So that means they're going to be going in opposite directions. One's up, one's down. And the coefficient on x cubed is 1, right? So it's positive. It's positive x cubed. So that means it's down on the left and up on the right. So as I go to -infinity, the function will be also going to -infinity. And as I go to positive infinity, the function will be going up to positive infinity. So I can kind of add that in. On the left side, my function is going to be going down. So again, you can see this crossing, right? If it's going down and this is the intercept of multiplicity 1, it's got to cross. So somewhere in here has got to be a turning point. Now, sure, I could plug in a value like -2.5, and I could plug that in to get a y value. That seems like then I could give myself maybe a location of this top. But again, for now, the general shape is what I'm going for. So you're welcome to do that, but you don't have to. And then this is already crossed. It's not going to come back down and cross again, or I'd have another x-intercept, which I don't. And we know that the end behavior is that it's going off to infinity. So I'm just going to go ahead and draw it going off to infinity. So we were able to put the clues together based on the multiplicity of the intercepts, the y-intercept, and the end behavior to get a picture of what this graph looks like. Not 100% accurate, but a very good start. The right shape for sure. Okay. So there are 2 more of these. I want you to go ahead and pause and work on number 2. It's already factored for you, so that's nice. And then unpause and I'll talk you through it. All right, so let's talk through the pieces and then I'll draw the graph together. So I have 3 intercepts. -1 and -4 are both multiplicity 1. So -1 and -4 are both multiplicity 1. I would expect that the graph is just going to cross. I can actually use that, well, I'll wait till I do all these pieces. And then x equals -3 is multiplicity 2. So here, the graph is either going to bounce from the top or bounce from the bottom, but it's not going to cross. My y-intercept is here at 36. So that kind of already tells me that this graph has to be going, that's not a very lovely picture, has to be going like this. Because again, it can't cross the x-axis at any of the places other than those we've already determined. So it has to be going up to get to here, which means I can almost already fill in what's going to happen in between. If it crosses, it's going to have to come down, which means when it bounces, it's going to bounce from the bottom and then come back up here from the bottom. So just using those powers of the pieces of the puzzle to put together. Okay. And the end behavior is up on both ends. So that also matches kind of what we're seeing here. So I could fill this in again. You know, how low does this go? I don't know. I could plug in -2. Whoops. Since that's right here, I could plug -2 into this and get a number. Let's see if I can do that in my head. Probably not. Let's see. So that if I plugged in -2, I'd have a -1 times 2 times a 1. Oh, squared. So that'd be -2. Okay. So if I was kind of doing these, it doesn't look like it comes down too far. Now, is that the lowest point? Can't promise, but at least I get some idea of about how low it might go in that area. And so I'm going to go ahead and call my graph completed. All right, you got one more to try. Go ahead, pause the video, and give it a go. Okay, how did it go? So this one is a little tricky. Well, maybe not tricky, sneaky. Because when I go to factor this, I pulled out the negative because I thought that would just make the rest of the factoring easier. And that gives me an x squared plus 16 inside. If I go to set that equal to 0, x squared plus 16 would give me x equals plus or minus 4i, right? Because I'd have x squared equals -16. And these are not actual intercepts. That means that the only intercept we have comes from the -x to the 4th equals 0, which will give you 0, right? 0 to the 4th is 0. And that has a multiplicity of 4. So it's going to pop up and touch and come back down, or could have come down and gone back up. My y-intercept will also be at that same 0. So the only intercept I have is this 0, 0. And so how do I know whether it goes like this as I've drawn it or like this? And that would come from the end behavior. Since the, oh, I wrote 4th because I factored it out. It doesn't change because it's still an even power and the coefficient, the leading coefficient is a negative. So that means it goes down on both ends. Now, it is possible that when it goes down, maybe it has a turning point somewhere here. So I really don't have a lot of information about whether it does this or maybe it does this, right? Because I don't have a way to find those values. So in this case, the most that we could do is know that it's basically all going to be down here, going to -infinity on both ends and touching at the x equals 0. So it's kind of a to be continued, because when you take calculus, you are going to be able to draw in the details of what's happening here much better.